Retro Ninjas, and welcome to another beautiful day. Today we get to talk about compound probability, and compound probability is simply the probability of two or more events together. Like when you make a compound sentence, when you keep talking and talking forever and ever, and you just keep going and going, and there's no actual end to it or no actual punctuation, but you just continue to talk without actually stopping and putting a period, and you just keep using the word and to keep extending that sentence. Compound probability. So for example, if we were to roll a die and spin a spinner, so that would be an example of a compound probability, because the die on its own has its own probability, and then the spinner also has its own probability. Now we have two types of compound probability. We've got a probability that is an independent event. The outcome of one does not affect the likelihood of the second. So when I roll a die, unless I'm throwing it at the spinner, the outcome of the die does not have an effect on the outcome of the spinner. So you get two events, event A and event B. And so if we look back at our example, we could say this was our die, and then event B would be our spinner. So the probability of both events occurring. So you get probability of A and B. So remember, that's our union symbol. So that's our union symbol. That is our intersection. So yesterday we talked about it as, oh man, I used a parenthesis and a quotation mark. So yesterday we explained it. We just counted on the spinner. It said it had to be odd and greater than 5. So we were able to just see those two things together because that was on one spinner. But now we're going to be dealing with two different events, and we've got to figure out that probability. So when A and B are independent, we're going to multiply the probability of A occurring by the probability of B occurring. So whatever the probability of A times whatever the probability of B. So 1 and 2, we're going to use the spinner on the left, and we're going to flick it. We're going to spin it. And then a letter from the word bingo. So we're going to do two simple probabilities and then combine them to get our compound probability. So the probability of a number less than 7. So we've got 6, 5, 4, 3, 2, and 1. And I did it again. Y'all see how that happens? Your brain is like, you just said 2. Let's write a 2. So there's 6 possible outcomes. That's our favorable. That's what we want to happen. There's 6 of them. And then there are 10 total outcomes. So that would be the probability that it's less than 7. And then selecting the letter B out of bingo, well, there's 1 B out of 5 total letters. So now we just get to multiply fractions. So we multiply straight across, 6 times 1 and 5 times 10. So we get 6 over 50. And of course, we need to reduce that fraction, and it would be 3 over 25. Now, of course, I could put that in decimal form, which would be 0.12, or I can put it in percentage form, which would be 12%. That's going to change depending on whatever it's asking for. Just be comfortable with all 3. Okay. So number 2, at least 3, and then a vowel. So at least 3 means we need all of our numbers to be greater than 3. Let's go ahead and erase the wheel. That's pretty satisfying right there. So 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes there because at least means 3 can be included. So now we've got 8 out of 10. For our first simple probability, and then because we want both of them to happen, we're going to multiply. There are 2 vowels in the word bingo, so I and O. So we got 2 out of 5 total outcomes. Again, we're just multiplying straight across. So 8 times 2 is 16. 10 times 5 is 50. Reduce that fraction, and we get 8 over 25. All right, we'll do one more. How about this? Number 5, because it's important. Because it introduces a word to us that we need to start to recognize. So number 5, a card is chosen at random from a deck of cards, replaced, then another is chosen. If you see the word replaced, that means you have independent probability. Because if we took that card out without putting it back into the deck, well, now we have changed the probability for the remaining cards. So that's what we'll talk about next is dependent. So I want you guys to see the word replaced or without replacement. So if we have replaced, we have independent. So a card is chosen from random out of a deck of cards, replaced, and then another is chosen. What is the probability of choosing a diamond? So there are 13 diamonds in our deck of 52 cards. So the first time we're pulling it, we got 13. That's out of 52. We put that card back, so the second time we pull, it's a 13 out of 52. We multiply that number straight across because that's what we do with fractions. We just multiply them straight across. And we get 13 times 13 is 169. 52 times 52 is 2704. Math frac that rascal, and we get 116. Now, I know you're thinking, man, that's some big numbers. Well, if you would have reduced from the jump, so we reduced that 13 over 52 to 1/4, we still get the same thing. So you can make your lives a little easier from the beginning and go ahead and reduce that. We'll do one more on this page together. Be a guest on the last 3 questions of a multiple choice test. Does that sound familiar to some of us? Guys, don't guess. Get it right, you weirdos. All right. If each question had 4 choices, what is the probability that she got all of them correct? So let's say be a guest on the first one. There's 1 right answer, 4 possibilities. That's a 1 out of 4 shot. Okay. Her next one, she's like, man, I got to guess again. Shoot. All right, let's see if I can get this right again. She's got a 1 out of 4 shot. And on her third one, she's like, man, just, it is what it is. See it all the way, baby. See through. So 1/4 shot. So and now her probability of getting all 3 of them right goes from 1 out of 4 to 1 out of 60. Okay? That's why, guys, on multiple choice, if you can eliminate answers, your probability is going to go up. You know what? Let's do one more. I'm feeling good. I'm liking it. I'm rolling. We in the rhythm. All right. Month of the year and a day of the week are chosen at random. Well, there's 12 months and 7 days, right? What is the probability that we choose a month that starts with J, so January, June, July, and Wednesday? So there are 3 months that start with the letter J. So that's 3 out of 12. And then we're going to multiply that by 1 out of 7, because there's only one hope day. Okay. Multiply straight across. 3 times 1 is 3. 12 times 7 is 84. You're going to go ahead and math bracket to see if it reduces. So we hit math frac, and of course it does, because 8 plus 4 is 12, and that's a factor of 3. And then we get 1 out of 28. So guys, that is independent probability. You know what? There's more on the next page. I didn't even need to do that extra one. Holy cow. 14 girls and 11 boys in Mrs. Haynes' homeroom. 9 girls and 15 boys in Mr. Jump's homeroom. Jumpman, Jumpman, Jumpman. If a student is chosen at random from each class, what is the probability that both are boys? So we look at the total number of boys in Mrs. Haynes' class, and that would be 11 out of 25 students. And then we take the total number of boys in Mr. Jump's class, which is 15 out of, what is that? 15 and 9 is 24. Multiply our fraction straight across. 11 times 15 is 165. 25 and 24 is 600. And of course, we need to math frac that rascal. And then when you put that into your calculadora, you get 11 over 40. Christian is guessing the 4-digit code in his parents' garage door opener. What is the probability that each digit is greater than 5? So it is imperative that we remember, when we see something like this, our numbers are from 0 to 9. So our possible set is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got 10 possibilities. It says, what is the probability that each digit is greater than 5? So we need to know, well, in this code, there are 4 digits that are greater than 5. This is a common probability situation. You will see this often. So in the first time he puts the code in, what is the probability it's greater than 5? Well, that'd be 4 out of 10. The second time, 4 out of 10. The third time, 4 out of 10. And lastly, 4 out of 10. So we just do 4 to the 4th, which is 256. Oh, 10 to the 4th, which is 10,000. Just put 4 zeros after that one. Math bracket, and we get 16 over 625. So guys, that is independent probability. One event occurring does not have an impact on the next event happening. It's not going to change the probability. However, when we get into dependent events, okay, when we get into dependent events, the outcome of one will affect the likelihood of the next. So you've got probability of both, and then the probability of the second after our first event occurs. So A and B are dependent now. So the probability of A and B. So you're going to take the probability of A and multiply it by the probability of B bar A. So this guy right here stands for given. So it is the probability of A times the probability of B given A did occur. So you'll see this, guys, a lot when you see without replacement. If you see, or in this situation, it's not replaced, without replacement, the outcome of our second event is being affected. The total number of outcomes is changing, which is going to change the way our probability works. Okay? So a bag contains 3 blue marbles, 10 green marbles, 4 yellow marbles, and 8 red marbles. A marker is chosen at random and not replaced. Not replaced, without replacement, all of that changes. It changes the total outcomes. Find each probability. So you want to know, what's the probability? So first off, let's see how many total daggone marbles are in that bag. So we've got 3 blue, 10 green, 4 yellow, and 8 red. So 3 and 10 is 13 plus 4 is 17 plus 8 is 25. So there's 25 marbles to start. Okay, so first off, we want the probability of red, then blue. So we're pulling a red. We're not putting it back. We're setting her off on the table. And we want the probability of pulling a blue. So probability of red, then blue. So the first thing, the probability of red occurring is there's 8 red marbles out of the 25 total. Okay, now we're putting that red marble on the table, and here's a big kicker. We are going to assume, I know I told you can't assume a lot in geometry, but we are going to assume what happened was what we wanted to happen. So we said, hey, I reached in that bag, I plucked out a red marble. That's going to come into play later, okay? So we're going to assume, hey, now that I got my red marble, the number of items, the number of marbles that are in my bag drops from 25 to 24. Now the second one, it wants it to be blue. And of course, we've got 3 blue marbles still. Now we just do our probability like we were before. 8 times 3 is 24. 25 and 24 is 600. Math frat gives us 1 out of 25. So look at 13 and 14. We're going to do those two together because it is important that we know if we're doing this, we are going to assume the event that we want to happen is exactly what happened. So the probability of both marbles being red. So I'm going to reach into that bag. I'm going to pull out a red marble. I've got an 8 in 25 shot of pulling out that red marble. Remember, we just said, hey, we pulled a red marble. We're putting it off to the side. Now the number of red marbles in the bag has been reduced. So instead of being 8 red marbles, there are now 7. And instead of being 25, because we pulled that red marble out, there's 24. 8 times 7 is 56 over 600. Math frac, and we get 7 out of 75. Right? And now look at number 14. Now we're going to say, hey, we're going to reach into that marble sack and we're going to get out both yeller. So the probability of pulling a yeller sack, okay, would be 4 out of 25. Because there's 4 yellow marbles. We have pulled a yellow marble. We are going to assume we pulled yellow. So now there's only 3 yellow left in there. And there's only 24 left. So 4 times 3 is 12. 600, we should know that number. We math frac it and we get 1 out of 50. Okay, but it doesn't just occur with marbles, but it will. It will often occur with marbles. It'll often occur with cards. Cards are going to be a big piece. You guys will have a piece of paper that helps you with cards. After the completion of a race, 75 runners were asked if they ran a personal best and if they trained. 22 said they had a personal best. 46 said they trained. Of those that said they had a personal best, 18 had trained. Man, that's a lot of information. It's almost as if we have a method that helps us organize data into a set. So if I come over here, that was a weird pace, and I draw me one of these, oh gosh, and I draw another one of those, you get this quirky looking Venn diagram that I kind of, wow. All right, so our universal set is runners. Okay, and of those runners, 22 said they had a personal best. So personal best was 22. And 46 said they trained. But remember, 18 of them had a personal best and trained. So that 18 is going to go in the middle. But because we can't double count them, we're going to take 18 away from both. So of the people that had a personal best, 18 trained, leaving only 4 who had a personal best but did not train. And of the 46 that trained, 18 of them had a personal best. So we subtract 18 from 46 and we get 28. And then, of course, there were 75 runners in this race. Well, something's got to give. So somebody didn't get a personal best or trained. I mean, that's what happens when you don't train. You definitely don't succeed. 75 minus 4 minus 18 minus 28. So the people that didn't get anything out of it was 25. They were just out there running for that free water, getting after it. All right, so what is the probability that the runners trained for the race but did not run a personal best? So how many total trained for the race but did not run a personal best? So we know that 28 individuals trained out of the 75. And then the probability that they did not run a personal best, we're saying, hey, 28 of those people trained. Only trained. They didn't run a personal best, right? So that's why that 18 is not included in the 46. Of those 28, we're going to say we got one that trained but didn't run a personal best. And now we're going to say 27 because we picked the runner we wanted out of 74. 28 times 27 is 756. Big boy numbers. 75 and 74 is 5550. Of course, we want to math frac that rascal because look at this. Look at this beautiful fraction. Okay, guys, and when we get to two-way tables, this data is going to just pop right out at you. But we're going to practice it without them because, you know, we got to be good. We got to be well-rounded, balanced geometro ninjas. All right, what is the probability that one runner had a personal best? 22 had a personal best out of the 75. And the other runner neither trained nor had a personal best. So that's our 25 slackers down there in the bottom. Remember, we found one already. So that's going to change the number from 75 to 74. 22 times 25 is 550. 75 times 74 is 5550. That's a lot of fives and zeros. I think it's like 111011. Sorry, I just insulted you in code. Okay, math bracket 11 out of 111. So guys, that is independent and dependent probability. Go be great.